Welcome to part 2 of BastionPg. In this part, we will focus on how BastionPg handles failover and recovery procedures for your high-availability PostgreSQL cluster. Make sure you have finished part 1 of this series, before moving on to this video.
Here you can see that Node 2 currently has the carp IP in backup state and a very high advertisement skew. Now we will bring down the complete container that hosts the master node. This would simulate a network segmentation or a catastrophic failure where the main server is no longer visible to clients. On the backup container, we query the interface again and you can see it has been promoted to master. This is done automatically by carp, without any involvement of BastionPg. We can tail the carp event log on the container, where you can trace the event that caused this server to be promoted. The client has been connected all this time, but when it detects the connection has been broken, it automatically reconnects and recovers state. Note that the client IP has moved from the main server to the backup server, without causing anything but a small reconnection cost. You can also notice that the second replication test database had been replicated from the master at the time of failure. Now we log into the new master server and confirm that there are no backup servers replicating from it at this time. From the client, we will now create a third test database before we stand the new backup server up. On the original master, let's power up the failed container. You can see that Postgres did not automatically start up, and that its carp interface was brought up as backup with a very high advertisement skew. This is because BastionPg adds special lockdown procedures for failed containers, to avoid data corruption when the container is brought back up. To reuse this container as the backup server, all we have to do is issue the BastionPg rebuild standby command, indicating the new master. Once we confirm the rebuild instruction, the system will create a new snapshot and immediately start replication from the specified master node. Also notice how the client is completely unaffected by the new replication node. From the newly promoted master server, we can issue a special query to verify that this new standby server is in fact replicating from this node. On the hot standby, you can see that all databases are correctly synced in real time. Now that our cluster is again in high availability, let's bring down the master server to see if the brand new hot standby will automatically take over. As you can see, the hot standby took over immediately and it now owns the master client IP. Notice the advertisement skew was automatically lowered to 0 instantly, preempting any other node within this network to take over as master. On the client, we can again see that the Postgres underlying client library is able to reconnect and recover state without any issues. Now we'll proceed in fast forward to restart the failed cluster and reconfigure it as a hot standby, leaving the complete cluster in the same state as it was before the start of this demonstration. We will also create a few more databases along the way, to verify that the replication is working on the new hot standby as well. After flip-flopping the masters and standbys a few times, you can see how easy and effective BastionPg is at helping you manage high-availability clusters with PostgreSQL.
This is the end of part 2. Thank you so much for watching. And we hope you enjoy this two-part series introducing Bastion and BastionPg. If you'd like more information on these projects, make sure to check us out on GitHub.